In this section, we're going to look at another strategy for integration called partial fraction decomposition. So essentially what we're trying to do, what we've usually done in the past is find a common denominator so that we can combine two fractions. Well, what partial fraction decomposition does is it basically works in reverse. I'm saying if this was the common denominator and this is what I ended up with, what two fractions could I have started with? And that usually leaves us with an expression that's easier to integrate. So let's look at an integral like this one. The antiderivative of 1 over x squared minus 7x plus 12. Well, what are some of the strategies that we could use? We could try to use u substitution. And the only real option here is to let u be the denominator. So we get a du here that doesn't really work. So u substitution's not going to work. We could try to see if this fits an inverse trig relationship. If that's the case, we could complete the square in the denominator, but we end up with 1 over x squared minus u squared, which is none of our inverse trig properties. So yet again, that one is no. The last real strategy that we have here, which is one we don't have to pull out very often, is using long division. Well, in this case, that doesn't make any sense since the degree of the denominator is bigger than the degree of the numerator. When would you want to use long division? And this is something we talked about last year. You would want to use this if the degree of the denominator is higher, because then we can set it up so that we can try and divide it out. When you divide this out, you'll be left with a couple of terms plus a remainder, and that might be something that we can integrate. But here, that won't work here. Another strategy that we could use is trig substitution, but we don't cover that in this class. Luckily, it's kind of gross. But so instead, what we could do is use the fact that this integral, that fraction, is equal to negative 1 over x minus 3 plus positive 1 over x minus 4. Those are both two really simple derivatives to take. However, how are we possibly supposed to know that those two fractions combine together to give us the 1? Well, this is where the strategy for partial fraction decomposition comes from. Okay, so step 1 is the last thing we just talked about. Divide when improper. If the degree of the numerator is greater than or equal to the degree of the denominator, use long division or synthetic division when possible. Remember, synthetic division you can only use for factors of the form x minus c. And then we can simplify the integrand that way. So if that doesn't work, then here's the step that we need to follow. First, we'll factor the denominator. Completely factor the denominator into linear and quadratic factors. You shouldn't have anything bigger than that. For each linear factor, the partial fraction decomposition must include the sum of fractions in the following manner. So we'll get into this form a little bit later, but if you have a repeated factor, like the first px plus q, then we have px plus q squared. If you have a squared factor like that, you have to repeat it multiple times in that way. This will make more sense when we do some examples. With quadratic factors, you're going to set it up as is shown right here. And I apologize if you can hear my dogs barking because I am at home. Okay, so let's work then with that same integral that we were working on. Partial fraction seems like a little bit of rule breaking, quite honestly, but everything is on the up and up when it comes to algebra, and it's a really great tool. So we're not even looking at an integral here. We just want to find the partial fraction decomposition. So the first thing that we want to do is rewrite this with a factored denominator. So that's going to be x minus 3 and x minus 4, which you could see from what we got before were the two denominators that we had. So here's what we know. 1 over x minus 3 times x minus 4. Each of those factors only appears once, so we don't need to worry about repeating anything with successive powers. We're going to set this up as it's going to be some number over x minus 3 plus some number over x minus 4. And that's the relationship that we are going to use. So the first thing that we do is multiply everything through by the LCM on both sides, x minus 3, x minus 4. This is going to clear all of the denominators. Well, on this side, everything's going to divide out, so we're left with 1. In this first one, the x minus 3 cancels out, and we're left with a times x minus 4, plus now the x minus 4's cancel, and we're left with b times x minus 3. Okay, so now we need to figure out possible values for x. There could be more than one correct partial fraction decomposition, which is why we can do a little bit of just guessing and finding a pair that works, because there are going to be more than one. We just have to find one that works. So what we do now is we choose values for x. We're trying to solve for a and b. We can choose any values for x that we want because we're going to maintain the equality relationship here. But let's think strategically. The first one that I would probably choose is to let x equal 4. If I do, then my equation becomes 1 equals a times 0 plus b times 4 minus 3, which is 1. So I essentially get that 1 is b. All right. Now we know one of them. Let's pick another convenient value. This time I'm going to choose to let x equal 3. So if I do that, my equation now becomes 1 equals a times negative 1 plus b times 0. Well, now that becomes 1 equals negative a, so negative 1 equals a. Is that the only way to decompose and find these values of a and b? No, but these are the ones that we found based on choosing some convenient values of x for ourselves. We only got to find one that works. So now we take all of this information, and that tells us that this fraction, 1 over x squared minus 7x plus 12, is equal to a, which is negative 1 over x minus 3, plus b, which we know is positive 1 over x minus 4. And so this is called the partial fraction decomposition. We're taking a single fraction and splitting it into more than one, but we don't want to keep the denominator the same, so we're trying to find two fractions that we could create a common denominator with to get the original answer. Okay, so that is sort of the process here. Okay, so let's put this in with some integration then. There's two cases. We can have distinct linear factors, meaning they only appear once, or we can have repeated linear factors. So we're going to cover both of those possibilities here, okay? So this one wants us to, again, find the partial fraction decomposition. Now I'm going to follow through with this one and integrate it at the end, even though it didn't ask us to, so that we can kind of see where we're going with this. So once again, we're going to go ahead and factor our denominator, and then we'll set this up with our unknown numerators to be able to find a possible way that we could decompose these fractions. So again, let's talk through the steps. First thing we're going to do is multiply through by x minus 2, x minus 3. This is what we get. And so this is the moment now where we get to take some liberties here and choose some values for x that we like. Well, I think that x equals 3 is going to be a good one. Do you see my strategy for choosing x's is to try to get either a or b to cancel out. So I'm picking values of x that make one of these quantities equal to 0. So if I choose that, then I'm going to get 1 equals a times 0 plus b times 1. So b is equal to 1 if I choose x to be equal to negative 3. If I choose x to be equal to positive 2, then I get 1 equals, this is going to be negative a plus 0b. And so again, we get a is equal to negative 1. It is just coincidence. That's what we've gotten both of these times. That's not always going to be the case. I should point out as well, this may not always be 1. We've got both the examples we did, the numerator was equal to 1, but that may not always be the case. And so now we can write our answer, the partial fraction decomposition. This is going to be equal to, oh, my pen went to sleep. A, which is -1 over x minus 2, plus B, which is 1 over x minus 3. And you may have that in reverse order, 1 over x minus 3 minus 1 over x minus 2. That's fine. Now, let's say that I wanted to then go ahead and integrate that. 9 times out of 10, what you're left with is going to be a simple log rule. That's not always going to be the case, but in this example, that's what we get for both of these. Even if you go through the motions of u substitution, u would be x minus 2, so du is just dx. So we're going to end up with the natural log, it's going to be negative because of that -1. The natural log of the absolute value of x minus 2 plus the natural log of the absolute value of x minus 3 plus c. And that would be that. So this goes from a fraction that we could not integrate using any of our techniques to now being able to split it into 2 smaller pieces that are something that we could apply our log rule to. Okay, the last thing that I want to look at is what if we have factors that repeat? All right, first, that denominator should have a plus. I don't know what happened to that when this got saved this year. X cubed plus 2x squared plus x. So we get that, and we factor our denominator, and we get x times x plus 1 squared. We get a repeated factor. Well, here's the way that we have to set this up. We have one linear factor that is non-repeated, so a distinct linear factor, which would be a over x. We need to have a single linear factor for all possible powers of the repeated factor. So this one goes up to squared, so we need b over x plus 1 to the first and c over x plus 1 squared. Let's say that was a cubed factor, then I would need b over x plus 1 plus c over x plus 1 squared plus d over x plus 1 cubed. You have to keep building up to that total power one at a time. From here, the process is exactly the same. So we're going to multiply through by x plus 2 squared. This is what we should get when we do this. Now, we can pick anything that we want for x. And what I'm going to end up doing, I'm going to choose -1 for x, and I'm going to choose 0 for x. Now, here's something we haven't seen before. We have an expression on the left in terms of x as well. We have to also plug that x value in over there. So I'm going to go ahead and do that. You can go ahead and pause your video and see if you can put those values in and see what you get real quickly. All right, so when I let x equal -1, I get that c is equal to 9. And when I let x equal 0, I get that a is equal to 6. All of that is great. The problem is that's only given me 2 of the values. I still haven't figured out b. So what we'll do for the last one now is let's use the fact that we've determined we want a to be 6 and c to be 9, and then we just need to pick another value of x. It may not cancel stuff out, but let's pick a number that is convenient. So I'm probably going to choose to let x equals 1, and I'm also going to use the fact that a is 6 and c is 9. Let's plug those values in and see what we get. When I do that, then b is the only variable, and I get that b is equal to -1. Now that we know all of this, we can build our integral. So our integral is going to be a over x, that's going to be 6 over x, plus b, which is going to be -1 over x plus 1, plus c, which is 9 over x plus 1 squared dx. Now from here, we can integrate all of these separately. So we're going to get 6 times the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1. This one, u is going to be x plus 1, du is going to be dx, but this ends up being the integral of u to the negative 2 du when we do that. And so that's going to give us negative u to the negative 1. So this will be minus 9 over x plus 1 plus c. That is what we get. So you can see, hopefully, doing these partial fraction decompositions usually leaves you with several very simple integrals to do if it works out well. So this is enough for you to get started. The last thing that we'll talk about tomorrow is quadratic factors. And so then you'll be able to finish the rest of your worksheet. I'll see you next time.